Building a Taylor polynomial. To build a Taylor polynomial, we're going to need the formula. So the nth Taylor polynomial of f of x centered at x equals a is the polynomial t sub n of x is equal to f of a plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a to the second power, and so on, all the way up to the nth derivative at a over n factorial times x minus a to the n. So this is the formula that we're going to be using to build our Taylor polynomial. And we want to remind ourselves that the degree of a Taylor polynomial, or a polynomial in general, is the highest exponent of x in the polynomial. The order n of a Taylor polynomial is the order of the highest derivative used to compute the polynomial. So often these will be the same, but sometimes these will just be slightly different, the degree versus the order. In this example, we're told a function f has the following properties. F of 1 equals 2, f prime of 1 equals negative 1, f double prime of 1 is equal to 1/2, and f triple prime of 1 is equal to 3. Find the second and third order Taylor polynomials for f centered at x equals 1, which is the better approximation for f of x near x equals 1 and y. So let's start by finding the second order Taylor polynomial. That means that the highest derivative we're going to use is the second derivative. So we'll start by saying that t sub 2 of x is equal to, I'll write it in general first. So the formula says that we're going to have f of a, f of the center, so that's f of 1, plus f prime of 1, and then it's over 1 factorial times x minus 1 to the first power, plus f double prime of 1 over 2 factorial times x minus 1 to the second power. So this is my second order Taylor polynomial, but I have to substitute in these values for f of 1, f prime of 1, and f double prime of 1. So f of 1 we were given is 2, so we have 2 plus, well, f prime of 1 was negative 1, and 1 factorial is 1, so we simply have minus x minus 1 to the first power, and then we have plus the second derivative at 1, which is 1/2, so I have 1/2, but over 2 factorial, and 2 factorial is 2 times 1, which is just 2, times x minus 1 squared. So what I end up with is 2 minus x minus 1 plus 1 over 4 x minus 1 squared. So this is the second order Taylor polynomial because the highest derivative I used was a second derivative. And it happens that this is also a degree 2 polynomial because the highest exponent of x I would end up with is an x squared. So now let's go ahead and find the third order Taylor polynomial. And that means that the highest derivative that we're going to use is the third derivative at 1. So what we're really doing is we're just going to go one additional term out. So I can go ahead and say this is t sub 2 of x, and that's part of my answer. But finding t sub 3 of x is simply going out one additional term here. So I'm going to go ahead and say that t sub 3 of x is equal to, I'm going to keep these first 3 pieces, so 2 minus x minus 1 plus 1/4 x minus 1 squared, but then the next one is going to end up looking like plus the third derivative over 3 factorial. So the third derivative, f triple prime of 1 over 3 factorial times x minus 1 to the third power. So I'm writing it generically first, but now I need to substitute in this value, which was just 3. So we're going to have this term is 3 over 3 factorial times x minus 1 to the third, and then I continue with all the remaining pieces. Those are still there. And then I can simplify the last term now to be, well, 3 factorial is 3 times 2 times 1, which is 6. So 3 over 6 is 1/2. So I have 1/2 x minus 1 cubed. So this is my third order Taylor polynomial, or t sub 3 of x. So it's going out and just finding that one additional term that's created using the third derivative. And then finally, we're going to answer the question, which is the better approximation for the function f near x equals 1 and y? Well, we know that adding on additional terms gives us a better approximation of the function. So the one that's going to be the better approximation near 1 is t3, because the more terms that we add to the polynomial, the better. To formalize that, we would say t sub 3 of x is a better approximation than t sub 2 of x. In this example, we want to find the third order Taylor polynomial for f of x equals the square root of x near x equals 1. So since we need the third order Taylor polynomial, we're going to need the third derivative of our function, the square root of x, and then we're going to have to substitute in x equals 1 to each of those derivatives. So we'll start by writing f of x is x to the 1/2. So its derivative is 1/2 x to the negative 1/2. The second derivative is going to be negative 1/4 x to the negative 3 over 2. And the third derivative of x is going to be positive 3 over 8 x to the negative 5 over 2. So we're just applying the power rule. Now we need f of a, f prime of a, f double prime of a. And our a value, our center, is 1. So we're going to have f of 1 is just the square root of 1, which is 1. And then here, if I plug in 1 to the negative 1/2, it will bring it to the bottom, but it's still just going to be a 1. So we're going to have just the 1/2. So f prime of 1 is a half. F double prime of 1 is just going to be negative 1/4 for the same reason, substituting in 1. It's just going to give us 1, so we're going to have negative 1/4 there. And the third derivative at 1 is positive 3 over 8. Now we can go ahead and start building our third order Taylor polynomial. So t sub 3 of x, in general, I'll write out, well, we were looking for f of 1 plus f prime of 1 over 1 factorial times x minus a being 1 to the first, plus the second derivative at 1 over 2 factorial x minus 1 squared, and the third derivative at 1 over 3 factorial times x minus 1 to the third. So this is the general formula, and then we substitute in the values that we found over here as scratch work. So f of 1 was 1, plus f prime of 1 was a half, so I get a half over 1 factorial, that's just a half, times x minus 1, plus, now we have f double prime of 1, which was negative 1/4, and then over 2 factorial, which is 2, times x minus 1 squared, plus f triple prime of 1, that was 3/8, so 3 over 8 divided by 3 factorial, which is 6, times x minus 1 cubed. And now it's just a matter of really simplifying these two coefficients. So the other two parts are fine, so we have 1 plus 1/2 times x minus 1, and then this is going to be minus, so here 1/4 divided by 2 is like 1/4 times 1/2, so we're going to have minus 1/8 x minus 1 squared. And then here, 3/8 over 6, well, that's 3/8 times, instead of dividing by 6 over 1, it's multiplying by 1 over 6. And here we can reduce, so we get 1 over 16. 1 over 16 x minus 1 to the third power. So this is my third order Taylor polynomial for f of x equals the square root of x near x equals 1. And just to tie it back to what we've been talking about, what was the point of doing this? Well, the square root of x is a transcendental function. So if I were to try to evaluate like the square root of 2, that's typically something I would plug into my calculator to find. But now this is an approximation for the square root function near 1. Well, 2 isn't super close to 1, but it's close enough. We could use this polynomial to approximate the value of the square root of 2 by simply plugging 2 into each x. So that's, well, again, what we're doing when we're finding these Taylor polynomials. The third order, because we use the third derivative, this also happens to be a third degree polynomial. In this example, we want to find the 6th degree Taylor polynomial for f of x equals cosine x near x equals 0. We're trying to find the 6th degree Taylor polynomial, so we are going to go up to using the 6th derivative here. At least, we want to make sure that we end up with the 6th degree Taylor polynomial. So we'll take 6 derivatives. So we have f of x is cosine x. The derivative of cosine x is negative sine x. The second derivative of cosine x is going to give me a negative cosine x. The third derivative is going to give me a positive sine x. The fourth derivative, and we stop using prime notation, is going to give me cosine x. The fifth derivative is going to give me negative sine x because we've now gone in a circle. And the sixth derivative is going to give me negative cosine x. Well, now we want to evaluate each of these at 0. So we're looking at f of 0, cosine of 0 is 1. F prime of 0, sine of 0 is 0. F double prime of 0, if I plug in 0 to cosine, I get 1, but there's a negative on the outside, so I get negative 1. The third derivative at 0, sine of 0 is 0. The fourth derivative at 0, cosine of 0 gets me back to 1. Hopefully we can see this pattern that's happening here. So we have now the fifth derivative at 0 is 0, and the sixth derivative at 0 is negative 1. So we have, again, cosine of 0 is 1 and a negative on the outside. So from here, we can start to build our Taylor polynomial. All right, so we're going to go ahead and say that t sub 6 of x is going to be f of a, well, f of 0 is 1, so I'm just going to start substituting in automatically. And then plus, so here we're going to have 0 over 1 factorial, and then x minus 0 to the first power. So that term's actually going to disappear. Plus, now we're going to have the second derivative at 0, so that's negative 1 over 2 factorial, and then we're going to have x. It's going to be x minus 0 every time, but that's obviously just x, so I'm going to leave this as just x squared. Then I'm going to have plus, the third derivative at 0 was 0, so we'd have 0 over 3 factorial, and then x cubed, but that's just going to give us 0. So 0 over 3 factorial is 0, so that term is gone. And then we'll have plus, the fourth derivative at 0 was 1, so we'll have 1 over 4 factorial, and then x minus 0 to the fourth. And then, you may have guessed, the fifth derivative at 0 is 0, so that term is actually going to be gone as well. 0 over 5 factorial x to the fifth, so that term is gone. And then here we're going to have the sixth derivative at 0 was negative 1, so we have negative 1 over 6 factorial, x minus 0 to the sixth. Alright, so we can see, what do we have left? We only have left the 1 and then all of the terms with even degrees. So we're going to have 1 minus 1 over 2 factorial is 2, so we have 1/2 x squared, plus, now we have 1 over 4 factorial. So 4 times 3 times 2 times 1 is going to give me 24. So I'm going to have plus 1 over 24 x to the fourth. And then we lose the odd degree, so we have minus 1 over, well, 6 factorial is a pretty big value already because factorials grow really fast. It's going to be 720. So we have 720 x to the 6th. So we do have, after using 6 derivatives, a degree 6 Taylor polynomial for cosine x near x equals 0. And so one of the things that I want you to just observe here is if I substitute in 0, well, all of these terms here are going to go away, and we know cosine of 0 is 1. So we can start to see that we have built a polynomial that does exactly represent cosine at 0 and then approximately represent cosine near 0. The other thing I would want you to notice is that since cosine is an even function, its polynomial representation should also be an even function, and we can see that it's consistent of terms that all have even degrees. So just some of the things to maybe notice about the polynomial representation or polynomial. In this example, we have t sub 4 of x is equal to this 4th degree Taylor polynomial for some function f. And we're working backwards here to find the value of a, f prime of a, f double prime of a, f triple prime of a, and the 4th derivative at a. So let's take a second to write the general formula for a 4th degree Taylor polynomial. So t sub 4 of x in general would look like f of a plus f prime of a over 1 factorial times x minus a plus, and so on, up to the 4th derivative evaluated at a over 4 factorial times x minus a to the 4th. So what we need to go ahead and do is compare this first term and the coefficients of all of these terms to find these missing values. So we'll start by finding the value of a. So here, the place that we're going to look to find the value of a is the binomials. So here we have x plus 2 squared, x plus 2 cubed up to x plus 2 to the 4th. So our value of a, we can see, is going to have to be the opposite of this second piece here. So it's going to have to be negative 2. So we're going to have x minus negative 2. So we can go ahead and list that one out as our value of a. And then from there, we want to go ahead and start to find f of a. Well, that one's actually not too bad because we can just align here. That first term is the value of f of a, or f of negative 2. So there's some function out there where when you plug in negative 2, you get out 2. And then we're going to go ahead and try to find f prime of a next. And that means we're going to look at this coefficient here. Positive 3 has to equal the f prime of a over 1 factorial. Well, 1 factorial is just 1. So it's actually kind of nice also for this piece. F prime of negative 2 is actually just 3. So we don't really have to do too much work for that. We can just visually compare the coefficients there. It doesn't start to get interesting until the next one, where we're going to look at the coefficient in front of x plus 2 squared. And so that negative 2 is going to have to equal this coefficient, f double prime of a over 2 factorial. So what I'm going to go ahead and do is set up a little equation there. So f double prime of negative 2, that was the value of a, over 2 factorial, well 2 factorial is just 2, has to equal, so this whole coefficient here has to equal the coefficient in front of x plus 2 squared in the Taylor polynomial expansion. So it has to equal negative 2. And then we're simply going to solve this equation, where to solve for f double prime of negative 2, I'm going to multiply both sides by 2. So f double prime of negative 2 is just negative 4. So that is the value of f double prime of negative 2. And we're going to move on and do something very similar for finding the 3rd derivative evaluated at a. We're going to compare, we're going to look at the coefficient in front of x plus 2 cubed, and that's going to have to equal the 3rd derivative at a over 3 factorial. All right, so let's go ahead and set up our little equation. The third derivative at a was negative 2, over 3 factorial, well 3 factorial, 3 times 2 times 1, that's 6, has to equal 1/3. So this coefficient in general has to equal this specific coefficient, and then we're going to solve for the third derivative at negative 2 by multiplying both sides by 6. So the third derivative at negative 2, if I multiply both sides by 6 here, to cancel these out, 6 divided by 3 is, and finally this last one, we're going to look at the fourth derivative evaluated at a over 4 factorial. That coefficient is going to have to equal negative 1/6. So they're the ones that go with the degree 4 term here. So setting those coefficients equal to each other, we're going to have the fourth derivative at a was negative 2, over 4 factorial. So 4 factorial is 4 times 3 times 2 times 1. So that's going to be 24. So we're going to have 24 over here is equal to negative 1/6. And then solving over here for the fourth derivative at negative 2, I'm going to multiply both sides by that 24. All right, so that these are going to cancel out. And then we'll end up with our fourth derivative at negative 2 is equal to negative 4. So 6 goes into 24 evenly as 4, and it was negative. So we have worked backwards here and found the values of a, f of a, and then all of the derivatives evaluated at a up till the fourth derivative.